Okay, so welcome everyone to start of this meeting. This is the 14th Global Workshop on String Theory. So this meeting is continuing a really long tradition of which some of us have been part in earlier years. We're also starting a new tradition because it's the first joint India-South Africa String Theory meeting, and we hope this will also establish a long tradition in this really wonderful setting. And so thank you to Vishnu and everyone else who did the organization here for getting us all here. And to start off this meeting, we have Anosh, who's going to tell us about a non-perturbative phase diagram of 2D anything to 2 to super Yang theory. So the talks are 45 minutes, and then we'll have questions. And we'll have 2 more talks after lunch, which will start at 1:30, and then we'll have 1 talk after dinner. Okay, so thank you.
Thank you, Surya, for a nice introduction. So it is very good to be here in this joint meeting between India and South Africa. So let's hope that the tradition continues. Okay, all right. So the title of my talk is Non-Perturbative Phase Diagram of two-dimensional 2,2 superangles. So this is pure superangles in 2 dimensions. So this is based on our recent paper, which was published here. So this is work done with Navdeep, who is a postdoc at Math Science in Chennai. So Navdeep was my second PhD student at ISA Mohali. Then with Raghav, who is at Jefferson Lab. Then David, who is at University of Liverpool in the UK. All right, so the question is about making use of lattice gauge theory. We can use it as a machinery for probing non-perturbative physics. So holographic conjecture, it has non-perturbative physics in it. So a version of the conjecture is telling us that weakly coupled gravitational theories in d+1 space-time dimensions is related to strongly coupled superangles in d, 1 dimension lower, in d space-time dimensions with the gauge group SUN. So this is also a strong coupling, weak coupling duality. Okay? So on one side, if it is weak, on the other side, it is strong, and vice versa. So we will be using lattice as a machinery here, and the gauge theory is strongly coupled. How do we study this? So how to study strongly coupled superangles? So at large and finite n. So we need to study at, say, a finite n, okay? N equal to 5, number of colors. So right now, we don't have any analytical tool to study a finite n. At infinite n, yes, we have, but at finite n, we need to go to numerical set, okay? Lattice, for example. So it's really hard. So we can use space-time lattice as a tool to study this. So we use lattice gauge theory, techniques from lattice gauge theory. Okay, so the question is about implementing a supersymmetric theory on a lattice. So if you look at the supersymmetric algebra, so here we can see Q and Q. On the right-hand side, we have P. P is the generator of space-time translations and infinitesimal translations. On a lattice, we don't have this notion of infinitesimal translations. So this relation is broken on the lattice. So naive discretization breaks supersymmetry. So it appears that supersymmetry and lattice, they are not compatible, but there is a clever way. Okay? When we encounter some difficulty, we will always find a way. So there is a way, there's a clever way to put SUSY on the lattice. So what we can do is we can combine space-time symmetry with the internal symmetry of the theory. And we combine them and we make use of what comes out of it to put this theory on the lattice. Okay. So the resulting lattice is supersymmetric.
Yeah. Basic theoretical question.
Yes.
Is there a way to fix this by using shift operators instead of generators? Like if you use either the I, P dot, make L where it is the lattice spacing,
Yeah.
using P, and then concepts of shift operators.
Yeah,
Does that work?
Yeah, you can use P as some kind of shift, right? Exponential of.
Yeah, exponential.
Yeah.
Don't you make shift a shift for the operators?
Yeah, that's what I was wondering. I don't know.
Yeah, I'm not aware of this. I don't know. Okay.
Because whatever Rasmus parameter appears, I guess the square, yeah, some quadratical, the and right. Yeah, but I don't know.
Yeah, that's a good question. So answer is no. I mean, I don't know. So we can think about it. Is this related to that clock shift symmetry?
You know, for instance, you can never realize the Heisenberg algebra in also in
Right, of course. Yeah.
You can realize the shift algebra, which is
Right.
shift
Yeah.
operators.
That may be possible. You know, David Mandelstam, he has some recent papers on that. So that may be possible. Okay, so this was introduced by Witten back in the days, from the concept of combining internal symmetry with space-time symmetry. So he used that back in the days to construct this Donaldson-Witten invariance for the case of n equal to 2 superangles in 4 dimensions, and find some deep structures in mathematics making use of that. Okay, so the resulting lattice is supersymmetric. So there is a supersymmetric lattice construction, but not for all kinds of supersymmetric theories. There are restrictions. So we can preserve a subset of supersymmetry at finite lattice spacing. So the condition is we need, in d space-time dimensions, we need 2 power d supercharges for this construction to work. So this condition is satisfied for this particular theory, n equal to 4 superangles in 4D. So in 4D we have d equal to 4, and 2 power d we have 16, and n equal to 4 superangles, it has 16 supersymmetries. Okay. So this condition is satisfied. This is a very interesting theory, and also dimensional reductions of this theory. And this includes this 2-dimensional 8, superangles, again 16 supersymmetries. And there are several other theories that we can implement on a space-time lattice. Okay, now coming to 8, superangles in 2D. So this, yeah.
Did you say how that works?
I will briefly mention. So we are coming to that. So coming to 8, superangles in 2 dimensions. So this has a well-defined holographic dual. Okay, this theory. So we can consider holography at finite temperature. And we can ask what happens at low temperature, what happens at high temperature. So the 2-dimension theory, it lives on a torus. It was boundary conditions. So there is the spatial direction is compactified, and in the dual gravitational theory, there also the spatial direction is compactified. So at low temperature, the gravitational system, it contains various types of solutions with horizons, okay, black solutions. So there is a homogeneous D1 solution, which is called a black string, and so this black string, it wraps around this compactified spatial circle. And there is a localized type of solutions, D0 solutions. These are like Schwarzschild black holes. So there are 2 kinds of solutions, and they have different topologies. And there can be topology changing transitions between the 2. So it has been well studied in the literature.
Just one second. This, the finite temperature phase will break supersymmetry.
Yes, it will break supersymmetry, but there will be remnants of supersymmetry, like the fields, number of bosons, fermions, and the dynamics associated with it.
But can't you study a phase which preserves all the supersymmetries?
But as soon as you introduce temperature, there is no SUSY is broken softly, right? So then you have to study the theory at 0 temperature.
Yes.
But we are interested in quantum black holes. Quantum black holes, they have temperature, they radiate. So you need to consider the system.
So you're saying you could study it at 0 temperature, but you're choosing to study it in a phase where SUSY is broken. It's not like inherently this theory has to be studied.
Yes, so we want to study, so we want to understand, we want to validate the duality language. Okay? So people have done several things on the string theory side. where the theory is weakly coupled. Okay? So they have made some predictions, calculations, and we want to ask, can we verify those predictions? Okay? And on this side, the theory is strongly coupled. And they did this for finite temperature. So, okay.
You're directing at 2,2, right? You're not 8,8.
Yeah, we are going to 2,2. I'm slowly introducing things. Yeah. Okay, now at low temperature, there's an instability. So we have this black demon brain, which is like a uniform string with a horizon. And if you tap it, if you give a small perturbation to it, and so there is an instability. Okay? And there will be wiggles and everything, and finally the string breaks into a spherically symmetric solution. Okay? So this is the Grigoriev-Laflamme instability. And there is a phase transition happening in the two. And we can ask, can we capture this transition in the dual gauge theory? Answer is yes. So we need an order parameter, since it's a phase transition. So the order parameter in gauge theory is the spatial Wilson line, which wraps around this the closed spatial direction. Okay? So we measure the spatial Wilson line, and its magnitude is serving as the order parameter of this transition. So there is a spatial deconfinement transition in the gauge theory. Okay, now coming to integral 2,2 superangles, GB. So here we are focusing on a gauge theory system with the lower number of supercharges. Okay? So there are only 4 supercharges in this theory compared to 16, the other one. So for this theory, holographic dual has not been constructed yet. Okay? Nobody knows what the dual is. So the question is, how much does it resemble to the 16 supercharged counterpart? It has a holographic dual, and how does the reduction in supersymmetry affect holographic features? Okay. So we can ask these questions on the gauge theory side, and we can see how the phase diagram changes, and we can give some input to people on the other side, okay, and they can construct the holographic dual, if it is possible.
Sorry? So earlier you said that the Witten trick works only when there are 2 to the D supercharges. Now 8,8 has 16 supercharges, which is a little bit bigger than 2 to the 2.
It's a dimensional reduction. So I also said dimensional reductions as well.
So the lattice you actually work with will have some 2 compact dimensions, right?
If you reduce from 4D to 2D, yes.
Right.
2 directions would be, you don't consider those dimensions, right?
Okay.
If you reduce them.
You don't get rid of the compact dimension of the lattice.
Yeah. Eventually you will get a torus. You put it on a torus.
Right.
Okay, so we can ask, how does the reduction in supersymmetry affect holographic features? So this theory is obtained from n equal to 1 superangles in 4 dimensions. So it has a gauge field, which is encoded here, and it has a gaugino, gluon and a gluino. And these are the degrees of freedom of this theory. So here we have a fermion, and there are 4 components for this fermion. For this fermion. So we dimensionally reduce this theory to 2 dimensions. And what we get is this 2,2 theory.
This 4-dimensional theory does not have a holographic. It's not holographic.
No.
Why do you expect it to dimensionally reduce if we get to?
No. The question is, I am not claiming that it will have a holographic theory. I am not claiming. Okay. So the question we are trying to answer is, we have some features for this theory, some holographic features that we capture in the gauge theory. Okay? And we ask, when we reduce the amount of supersymmetry, when we go to 2,2, how does those features change? How do they change? That's the question we are asking. Okay? And can we say something about the spatial deconfinement transition in the gauge theory? And what does that imply if there is a dual on the other side? So like I said, dual has not been constructed yet. I don't think we can rule out that.
Well, the most basic question is the operator dimensions. If there's a large gap in operator dimensions, then you expect there will be. So it's just a question of when you take the gauge coupling to be strong, then when you look at the operator dimensions, you get a large gap in operator dimension. And if you do, then you expect there will be a load. If you don't, you expect there will not be a gravity load, and you expect need load.
Okay.
So has this been analyzed? Like what happens to operator dimensions?
On the gauge theory side, that I'm not sure. You mean like whether there is a mass gap, things like that?
Yeah, so I mean in equal flow, what happens is that except for the graviton version, which is the stress tensor, everything else just gets a big anomalous dimension. And so that's why you're left with a few lightning is afraid when you have a gravity. The question is if that happens here as well.
Okay, yeah, I'm serious, I don't know, but something to.
Here the ring is equal from 4D.
Yeah.
And everything is a common theory.
But I think you can think of this purely from the gauge theory viewpoint, right? You have some prediction of n equal to 8, and you are asking how does that prediction compare to n equal to 2, right?
Yeah.
Without invoking holography at this stage.
I see. So sorry, actually this is one more basic point. Yeah, it's not even there. We don't even have it's not even a CFT.
Yes, not necessarily. Yeah.
So this is
It doesn't have to be a CFT, right?
Holography or motivation.
The lower dimension theory 8,8, it's not a CFT.
It's a motivation. I think your analysis will be in the gauge theory, right?
Exactly. I'm not going to the string theory
gauge
side.
transition,
Yeah.
which in this higher supersymmetric case corresponded to greater than alpha.
Yeah. So we are we are analyzing the theory with the lower number of supersymmetrics, and we are giving input like what we see there. Okay? With that, can a supergravity person construct something?
and this is still asymptotically free.
It should be, yeah. I mean, it's a supersymmetric theory. Yeah.
So, can you also think of it as turning on some mass deformations for utilization of it?
In the continuum, you cannot put a gauge mass. It is not allowed by the symmetry of the theory. But on the lattice, it appears. Because lattice has less symmetry. It has hypercubic symmetry. So a gauge must be
going from the higher supersymmetric theory from the n equal to 4 theory to n equals to 1, you can imagine that you turn on some masses for the free, and it's one chiral multiplets in the.
No, there are some. This is a pure. It's a
Yeah,
pure.
so once you turn on the masses in the n equal to 4 theory, you reach this at low energies.
From n equal to 4.
Yeah.
Yeah, you can break supersymmetry one by one, and you can reach n equal to 1 and 40, but that's a totally different field, right? I mean, it has many more fields.
But low energies, then the mass.
Yeah, you can deform like this
This is the
n equal to
theory
1
that's-
star deformation.
That's what I mean. That's
2
the
star, they are all possible. Yeah.
That's the theory that you have studied. So the n is 1 star. Oh, sorry.
Yeah, so from n equal to 4 superangles, yes, you can break supersymmetry. You can get n equal to 2 star, 1 star,
Yeah.
But the Lagrangian will contain more terms coming from this additional scalars. Okay. Now let's look at the symmetries of this theory. So we are looking at Euclidean spacetime. Okay? So we are rotating, going to Euclidean spacetime. So our Lorentz symmetry is this, SO4, which is the Euclidean rotational symmetry. The reason why we are going to Euclidean is we want to put it on a lattice, and so far, it's easy to put things on a Euclidean lattice. Minkowski lattice, I don't think anybody wants to. Okay, and it has a U1 symmetry, which is a chiral symmetry, okay? which is the R symmetry of the 4-dimensional theory. You can rotate the fermion in this way, which is a symmetry of the theory. So now let's reduce this to 2 dimensions and think about the twist. So reduce this 4-dimensional theory to 2 dimensions. Symmetry group becomes this. So the 4-dimensional Euclidean rotation becomes a 2-dimensional Euclidean rotation. SO1, 1, here it is SO2. Okay? And the chiral symmetry of the 4-dimensional theory, it is already there. Nothing happens to it. but I simply wrote this as SO2. Okay? U1 is equivalent to SO2. And we have an additional internal symmetry coming from the compactified directions. Okay? So there is another SO2, which was part of the original four-dimensional rotational rotation group. Now it has become an internal symmetry group. Okay? So what this means is we can rotate the fields internally. They are not dependent on space-time. So this is the symmetry group of this particular theory in 2D. Now coming to I mentioned about combining the space-time symmetry with internal symmetry. Okay? So we can combine this space-time symmetry with this, or with this internal symmetry, or space-time symmetry with this internal symmetry. Okay? So there are two possibilities. So in the literature they are known as A-type and B-type. Okay? Twists. A-model twist, twist. So what we are going to
standard prescription that you need to do to put the theory on the lattice, you have to twist it first.
So the advantage of this prescription is it preserves a subset of supersymmetry on the lattice.
This is what you mentioned in the beginning.
Yeah.
Are you going to explain this prescription? How you combine these things?
I will not go into details, but I will give details of how fields look like. It's similar to angular momentum algebra. You combine angular momentum.
So it's not able to explain the idea because you said Q alpha dot plus sigma alpha dot alpha
Yeah.
helium.
Yeah.
We couldn't realize that. So
Yeah.
now, if you twist, how are you able to realize it?
So I'm coming to that. So there are two options. So what we are going to do is we will combine this with this. Okay, that is the B model twist. So we define a new rotation group, okay, which is defined in this way. Take these two SO2s and take the diagonal subgroup of that and declare that as the new rotation. Okay, so this is what Witten did back in the days for integral to superangles. So this new rotation.
But in Witten's approach, this made the theory topological.
He restricted the theory
the
to
parallel sector and that sort of thing.
yeah, he restricted to topologies.
But not
So
so
that-
that you care about the full theory. You're not going to be talking about topological.
No, I'm talking about the full theory. Okay, we will not restrict our observations to topological observations. We just twist the theory. So this new rotation group, it is called the twisted rotation. Okay. So now what happens to superchargers and fermions and bosons of the original theory? So under this new rotation group, the supersymmetry charges Q alpha and Q bar alpha dot, they become, so there are four of them, and they become these four entities. There is a Q, there is a QA, and there is a QAB, which is minus of QPA, which is antisymmetric. So there is a Q, there is a Q1, there is a Q2, then there is a Q12. Okay. So these are Grassmann objects, so the fermions, they decompose in the same way as these supersymmetric charges. So we have a fermion eta, which is a Grassmann object, but these are integer spin objects. Okay? So spin 0, like that. Then there is a psi1, psi2, then there is a chi1, 2. So these fermions, they have several names in the literature. So they are known as geometric fermions, or Kähler-Dirac fermions, twisted fermions. Then in the lattice gauge theory language, they are also known as Kogut-Susskind fermions, staggered fermions. So they appear in various names. And they are highly tied to, you can express this using differential geometry language. These fermions.
So you write QAB, but it is a scalar, right?
QAB, it's like a two form.
In 2 dimensions.
Yeah, it goes like P forms in. It's an upper limit on P. I think it's D, number of dimensions.
Yeah, but in the 2 dimensions to form only like
Just a scalar, but it has a specific property. It has to be, say, epsilon AB. It has.
Like a pseudo
Yeah, it's a pseudoscalar. Yeah, that type of property. Yeah. Okay. Now, what happens to bosons? So, in the bosonic sector, we have a gauge field, which is in 2D, and there are two scalars. They are coming from the dimensional reduction of the 4-dimensional gauge field, and we can combine them into a one single gauge field, which is a complexified gauge field. Again, this is what we did for this potential case. Okay, now we can twist. I'm not giving the details, how exactly component by component it is, but we can find that mapping. It's available in the literature. So we can write the action in this particular form, Q acting on something. So Q is this supercharge, which we can call scalar supercharge. Okay? It acts like a scalar, but it's a Grassmann object. Then this is a vector supercharge, and this could be a tensor supercharge, okay, depending on the number of dimensions. So we can write the action in this particular form, Q acting on something. Okay? So in the differential geometry language, this something is called a gauge field. So when Q acts on these twisted fields, we get the action. And in the scalar supercharge sector, this is the supersymmetric transformations. And there are similar transformations for QA and QAB. I'm not writing them down. So Q acting on a boson, we get a fermion, and Q acting on a fermion, we get a boson, like that. So supersymmetry is preserved. And here D is an auxiliary field, it crosses, it is introduced to cross the object. Okay, now we can write the action of this two-dimensional theory in this way. So these are all twisted fields. It has very nice structure. So here lambda is proved coupling. And this action is invaded under Q supersymmetry. Okay? In the continuum, this action is invaded under all supersymmetries. Okay? Under Q, QA, and QAB, you can act on this and you will get zero. Up to equations of motion. So this is what is important for us. Q acting on S is 0. That is coming from the fact that Q squared is 0. And Q with Q gives you 0. So if you come back to that equation I showed earlier, Q alpha with V bar alpha dot, it was P. Okay? So somehow we massage that into this particular thing. So there is no translation on the right hand side. Okay? So we can make use of that property to put this action on the lattice. And all other, the remaining ones are broken on the lattice. Okay? Once we put them QA and QAB, they are broken on the lattice. Only Q is preserved, a subset.
This can be thought of as turning on some background for the art symmetry, right?
I don't know. In which way? How would the supersymmetry change?
So, usually when you have this, well, I guess maybe that is irrelevant when the space is curved, if the space is flat.
Here it's flat. Yeah, we are looking at flat Euclidean.
Okay.
So in flat Euclidean twist.
This is just the trivial one. But
Yeah.
in the curved space, if you have spin correction, you want to cancel.
Yeah, you will pick up
spin
additional
correction,
things. Yeah.
absolutely.
Yeah. So in flat Euclidean twist is nothing but a change of variables.
Yeah.
Just three-level things. That's it. Okay. Now let's come to the lattice action. So how do we put this on the lattice? So you have to put them in a very nice structured way. Okay? So the fields, they live on various places. So this is a unit cell of the lattice, and this cell is repeated itself, okay, through space and time. So the scalar fermion, eta, it lives on a side, okay, and the vector fermion. So we have two of them, psi1 and psi2. So they live on the links, okay, in a certain direction, and the other one, chi12, the pseudoscalar, which lives on this diagonal line, okay, with certain orientation. And the bosons, they also have orientations. Okay? So when we put QCD on a lattice, we put all the fermions at sides. Okay? They live on sides. But this is a particular lattice construction. It is a supersymmetric lattice construction where the fermions are P forms and they live on the P cells of the lattice. Okay? So this one, it lives on the 0 cell and 1 cell like that. Okay? It spills out the unit cell. Okay? Yeah.
Is there a intuitive reason that a pseudoscalar can live on a diagonal line?
Because it has two indices, right? 1, 2. Chi1, 2.
Oh, I see. Okay.
So that is why, yeah, it contains both 1 and 2.
So like, for example, F12, I usually think of as associated to an entire bracket.
You mean the field F?
Yeah.
It is. In a sense, it is, right? It contains both 1 and 2 components.
I see. You're saying that you can either think of it as a placket or the diagonal as a
Yeah. So, yeah, so it's so the unit cell. Yeah, so you have the edge, you have the edge, you have the corner, and you have the full thing. Right? For these two details. And we can for the anequiform superangles, there will be a similar unit cell which will be a 4-dimensional hypercube. And the fermions, 16 fermions, they fill out one by one. So there will be a scalar fermion which is at the corner of the unit cell. Then there will be this psi air fermions, and there will be 4 of them on the 4 edges, and slowly they fill out the entire unit cell.
Do you then integrate these fermions like you do with a Wilson line for the gauge field? Is that what you
Integrate, sorry?
integrate over the edge? Or like when you associate the gauge field to an edge here as well? Like you
Yeah,
feel
the
it
gauge
as
field is mapped to this link field. Okay.
Do you also do something like that for the fermion?
No, fermions, no, we don't do that. No.
Even if you did an exponential integral, it won't change anything.
Yeah.
Fermion.
It's a fermion.
The arrows.
What are the arrows?
So arrows, they have a meaning. Okay, we need arrows to preserve gauge symmetry of the lattice. So when we construct a lattice action, a gauge invariant lattice action, each term in the action should form a closed loop in the lattice. Okay? And so each term is given by these ingredients. Okay, and they arrange in a certain way that it is a closed loop. So that's
U1 bar the other way. So U
Yeah.
bar and U2 bar. I see.
exactly, yeah. So that is needed to preserve gauge symmetry because there is a trace, right? Trace X, Y, Z, and so they have to arrange in a certain way so that it's a closed loop.
So is U1 bar the diagonal of U1?
Yeah.
Is there a doubling problem here?
There is no doubling problem. That is very important. Okay? This construction, it avoids the fermion doubling problem. That is another beautiful thing about this construction. Okay? Anequiform superangles, you can put it on a lattice without no fermion doubling. So here also no doubling problem.
The doubling problem is very basic because you laticize the momentum, and
Yeah.
when you have P and N minus P, that's the same somehow. So why is
Yeah.
that? How can you avoid that doubling problem?
So you can invert the Dirac operator, the corresponding Dirac operator here, and you can see that from its structure that there are no doublers. So usually doublers are coming from the solutions. There are solutions at the edges of the unit cell, and only one solution is unique. All the others are spurious. We don't need them. They are some entities living on the lattice. So these are doublers, and they appear because of the discrete structure of space-time. Okay? And this is a big problem in theories with chiral fermions. You cannot discretize theories with chiral fermions without encountering doublers. Okay? You have to do something. So here, so somehow you have to get rid of the doublers. So people do many things. The first person who tried to solve this issue was Wilson when he introduced his lattice action back in the days. He introduced a master which is inversely proportional to the lattice space. Now as lattice space equals to 0, these doublers, they will become infinitely massive and they decouple. And there are other ways. There is domain wall fermions. Yeah, several ways. But you have to sacrifice many things. Like if you add a mass term, similar to what Wilson did, chiral symmetry is gone. Okay? So for each one, there is a no-go theorem, and if you try to circumvent that, you have to sacrifice it. Yeah. So here there are no doublers because we need all those doublers. They are the real fields of the source.
So you add only half the fields and you get half the field. That's what you're saying.
That is not the way. We need, I mean, all the fields are there. So there are 4 fermions, right?
Yeah.
There is eta, psi1, psi2, and chi1, 2. There are 4 fermions. And we need all 4 of them. They are part of the supersymmetric theory.
One confusing thing for me is that none of the fermions seem to spin off. They're like scalars, vectors, and pseudo-scalars.
Yes, they are components of spinors.
I see. So the answer is not.
If you take a direct spinor, it has 4 components, right?
Uh-huh.
So you pull out those 4 components and rearrange them, take linear combinations. What you get is this. Okay. So there is some kind of scrambling going on internally within the spinor. So that is what this is.
Where do Chi1 and F1 have opposite arrows?
Again, the gauge invariance. We will come to that. Because Chi1, if you look at the lattice action, see.
The minus in the.
Yeah, exactly. So it has to form a closed loop. Okay. So this is the lattice action. So if you put this on a space-time lattice, the action looks like this. So there is a Tooft coupling which is on the lattice, a lattice version of the Tooft coupling, which is related to the continuum Tooft coupling. And N represents the lattice side. Okay. N has 2 ingredients, N1 and N2, because it's a 2-dimensional lattice. And we have to sum over, this is the integral basically, integral V2x. And there's a trace is there, and all these objects, they have orientations. So each term is a closed loop. If we look at these orientations, they form closed loops. That is needed for gauging. Okay. And the observables you measure on the lattice, they have to be gauge invariant. If they are not, you will get 0. You cannot measure this. Okay. So this action itself is an observable. You can measure this. Okay.
So is it? I mean, what allowed this construction is the existence of a scalar supercharge. Is that?
Exactly.
But then,
So scalar supercharge is preserved on the lattice.
so a topological twist would do that, right? So for example,
But then,
N equals 2 in 14 would also work.
Sorry?
N equals 2 in 14 would also work.
No, it has some problem. It has,
Because topological twisting can be done. Scalar
yeah,
supercharge
any
can
of the
be
2
twisted.
in 4D, the dominant configurations are instant on, it's about the instant on configurations. There is something about the instant ons in this theory. There is a problem. Okay? So I don't know exactly, I don't remember exactly.
Okay. Is it expected that in the continuum limit you will recover the full supersymmetry?
That is expected, and that has been shown in one of our previous works. So you actually recover the full amount of supersymmetry and full rotational symmetry as we approach the continuum. So same thing when people construct a QCD on the lattice, they ask the same question. We have crystal symmetry on the lattice. Can we get the full Lorentz symmetry? And the crystal symmetry is good enough to recover, to turn into rotational symmetry individually. Yeah. So here also, yes, we can. Okay, so this lattice action, it is supersymmetric, it is local, it is gauge invariant, and it is free from fermion properties. It has all these nice properties. Okay, now, so putting this on a lattice, we impose periodic and anti-periodic boundary conditions. So on the spatial direction, we impose periodic boundary conditions for the fields, and the temporal direction anti-periodic, because we are looking at a finite temperature system. So the extent along the temporal direction, it is the inverse temperature of the system. Okay? So there are 2 extents, one along the spatial direction and one along the temporal direction. Nx and n tau, these are the number of lattice sides, and A is the lattice spacing, all those things.
So is the square lattice crucial here?
Sorry?
Can you have different lattice spacings in the 2 directions, or is the square lattice crucial?
I mean, let's go for simplicity. So this is the simplest thing we can have, but we can have 2 different lattice spacings along 2 directions. That would make our numerical computation complicated, but physics will not change. Okay, so there are 2 dimensionless couplings, which is given by this on tau and 5 minutes? No, you can ask lots of questions. So there are, I will leave it up to you. Okay, so there are 2 dimensionless couplings in this theory, R tau and Rx. The Tooft coupling in the continuum is lambda, it is related to the lattice one via this relation. Okay. There is also another parameter which is called the aspect ratio. behave, the ratio of the extents along two directions. So we perform simulations at fixed r tau and times. Now, how do we simulate this theory? Okay, big question. So what we do is we make use of path integral Monte Carlo. Okay.
They don't have sine problem?
That is another thing, we have to look for that. Yeah. We can ask whether this particular action, whether it has sine problem or not. Okay. And it has a very mild sine problem, so it should be okay. Yeah.
What is very mild sine problem?
Means so sine problem is telling you, you look at you integrate the fermions, what you get is the Dirac operator, which is roughly, it's like a matrix. And you ask how complex this matrix is. You compute the determinant. So you can write this as the modulus times a phase. Okay? And e power I theta. If theta is very close to 0, it's a mild sine wave. If theta fluctuates a lot, it's a sinusoidal object, right? Then it has a severe sine problem. And then you cannot measure your observable relative if theta is large. So for this theory, theta is very small. We measure that actually. There's
Like what about the measure? Because like if you do the integral of fermion integral in different orders, you get.
so here we are not doing fermion integral. What we do is we integrate out the fermions from the theory, and what we get is a Faffian or a determinant, depending on. And we deal with the Faffian. In our case, it's Faffian. Okay, so this integral has large dimensional integral over all fields, and here we have a spatial integral. Okay? And how do we implement this integral on a lattice? So let's look at a simple example. So let's look at path integral for pure angles with SU3 gauge group. Okay? Yeah.
So when you have this type of integral set up on the lattice, the fact that it came from a supersymmetric theory after twisting doesn't really matter anymore.
It doesn't really matter.
So the reason you do that is because you want to learn about supersymmetric theory.
But the structure, say the structure of the Faffian, it is heavily dependent on the fermions.
Yeah.
So this thing, it depends on the theory. It's coming from what the structure is. So if you look at a simple theory, pure angles with SU3 gauge group, the partition function is given by this. And let's think about putting this on a lattice. Okay? Consider a hypercubic lattice because this theory lives in 4 dimensions. And say 10 lattice in each direction. Okay? And the gauge field is mapped into a link field, okay, unitary matrix. And this SU3, so there are 4 link fields along 4 directions. And each link field is determined by 8 parameters because it's SU3 adjoint, okay, n squared minus 1. So the dimensionality of this simple integral is this much, okay, 320,000. That is a huge integral. And now coming to the real life lattice QCD solutions where people compute, decay rates and masses of exotic particles. So they do lattice simulations with 256, in one direction. So that's like a huge integral. Okay. So no computer can do that integral as of today. So we have to look for probabilistic methods. So large numbers, they're telling us that we need some kind of statistical or sampling method, okay, to deal with the system. So we use Monte Carlo sampling. So we will use a bit sophisticated version of the sampling method, which is the rational hybrid Monte Carlo. So rational is when you integrate out the fermions, you get Faffian power some rational 1/4 or something. Okay, that's the reason we use this. But this algorithm exists, and we can make use of that. And our code is publicly available on GitHub. It is also C lattice. You can download it, and play with it, and do many things, many types of things.
So if you did not have any of the fermions, just have the gauge field integral, that is just a solvable theory, right? That's the area of the
Yeah, you can. For example, in 2D, you can get results in terms of some Bessel functions, etc.
Yeah, I mean, so this has been treated in various ways in the literature.
Yeah.
So can that not be borrowed somehow? Can those results not be borrowed?
And implement that
you
along
integrate the
fermions.
fermion out and then
Maybe possible, but nobody has thought about it. It's a good point, especially along these lines of tensor networks. There are some analytic results, people borrow them by different solutions. Okay. Yeah, so coming back to our theory, maybe I finish first. Spatial deconfinement transition, it signals topology changing transition between black string and black hole geometries in the dual system. So what we are, the observer we are using is the spatial Wilson line, unitarized part of it because the link field was complex.
So what's your lattice spacing for these cycles? I mean, what's your lattice size for these
So
cycles?
the highest, it's not that much. It's I think 32, something like that.
And what rank is your gauge group?
We went up to 12 or 16. I don't know. Again, it's not that much. It's not 50 or. Again, computing power. So we used supercomputers in 3 different countries. Okay, so then we also monitor the Polyakov loop, which is given by this. Then the calculations, the lattice calculations, they need to remain in the deconfined phase for the Polyakov loop. So roughly between 1/2 and 1, normalized to admit a holographic dual interpolation. The question is about these contractible loops. So there is, whether there is a horizon or not in the dual interpolation. So these are our results. So this one is on 12x12 lattices with the gauge group SU12. So this is a spatial Wilson line. So it has a nice transition happening here. And this is a temporal, this is a Polyakov loop along the temporal direction. So a transition is happening around here. R tau, which is the dimensionless inverse temperature, around 0.85. And in this region, it is thermally deconfined. Okay, coming from here. And so
the WU and PU again, the Polyakov loop and the
along the spatial direction and one along the temporal direction. So there are two cycles, right, of the torus. Okay, so we want to pinpoint this transition, and also we want to find the order of the transition. Okay? So we looked further into it. So we looked at the susceptibility of the Polyakov loop, which is given by this, and the plot is like this. Okay? So it peaks at the transition. So from this we can extract the R tau value or the inverse temperature, which is 0.85 with some error bars, which is given in the paper. So these parameters are introduced to control something called flat corrections. Okay? Unstable. Sorry?
This is deep.
This one in 1 units. Yeah. I introduced the dimensionless unit somewhere in terms of flip-flopping. Here it is. Okay. In terms of beta. So things have to be dimensionless on a lattice. Put things on a computer.
What is the significance? Is there some significance of this 0.85?
We don't know. Maybe on the gravity side there may be. Yeah. So next question is, what is the order of this transition? So for that we need to borrow the ideas coming from condensed matter theorists. Okay? So they came up with many suggestions. So we can look at the n dependence of this susceptibility, how n scales. Okay. So if we fit the sky in this way, where n is the number of colors or number of degrees of freedom in our case. So for a first order transition, it should scale like n squared. Okay? And for a crossover, the peak height is independent of it. For example, crossover happening in QCD. And for a continuous second order transition, this coefficient p should be between 0 and 1. So we can measure this. So we measured this from our simulations. So what we get is 0.61 with some error bars. Okay. So there is a continuous second order transition for this particular theory. And compared to the 8,8 theory, the transition there is first order. Okay. So there is a difference.
Sorry, I didn't explain the second. How did you see the second order?
So we measure, we ask how the height of the susceptibility, how it scales with the number of colors. essentially how it scales with the number of degrees of freedom. And the scaling is something like this, generally speaking. And for a first order transition, it should scale like n squared. Okay? And for a crossover, there shouldn't be any independence. And for a continuous transition, it should be between 7.
So, like for third order transition, what will be?
I don't know.
Also, can you?
Continuous means second order and higher.
You can't
Okay,
just,
any continuity.
since you're computing the action,
What?
since you're computing the action, can't you compute, the free energy and its derivatives and
No,
see
you
that-
cannot compute free energy using Monte Carlo
I see why.
because there is an exponential minus s, right?
Yes. But you
So,
evaluate the
because free energy is coming from the partition function,
Yes.
so you cannot compute partition function in Monte Carlo situations.
But are you
Because-
computing the e to path integral or e to the minus s at least? You compute everything?
See that thing, so the entire thing is scaled by the partition function. Okay, so you cannot compute partition function itself. You can compute observables because that's already normalized by the partition function.
But
So
this
that
is also the derivative. So this is also normalized by the function. It's like the
so
derivative.
there is a way to compute free energy. So the way is from this you can do the inverse trick. Okay, so you need to do a numerical integration. So you get the results, say for internal energy, and from that you have to numerically integrate your
Actually, for the second order, that's all you need. You only need the internal energy. You just want to check if that's continuous. The free energy will be continuous. You actually want its derivative.
internal energy you can measure. Okay? So, but we took this approach. We took this approach of measuring this.
How do you read off Chimax from that?
Again, you have to be careful. How to find the maximum here. So one way is finding it from here. Look at the inflection point where the curve turns, and so we use both methods.
It looks divergent, right? At the
No, here the slope changes, right? You can fit this to a sigmoid, for example. Okay, so you do some kind of
in your
fitting
next plot, when you're showing the chi plot,
here.
is that divergent at 0.85?
It is supposed to,
Yeah.
So we
what's
look for.
Chimax in?
I mean, there are errors. That's what I put, roughly. There are errors. You cannot exactly pinpoint errors because you don't have enough data in between. So you have to roughly.
I think it's not supposed to be divergent with proportional to n squared.
Oh yeah, I'm sorry.
Yeah.
Yes. It's proportional to This is the relationship.
So, Anosh, as you said in Monte Carlo, you can compute observables because it's normalized by the partition function.
No, all observables are normalized by the partition function. What
Yeah.
we compute.
Yeah. So
Yeah.
how does that help? That the fact that it's
No, what I'm saying is you cannot compute partition function itself.
I'm asking why. You said
Because it is a sampling method. So it is a Markov chain. Okay, you start with some random place, and you apply. You jump. So
in
that
particular, I'm asking why can you not compute the partition function and why, but you can calculate the observables expectation. You said that's because you are dividing by the partition function. I'm saying why is that relevant? Because the way you would have do that is you have to compute numerator, then denominator, and then divide, right? You cannot do that at every sampling.
So you are multiplying and dividing by some common factor which we don't know. Okay. So when you compute an observable, it's already taken care of. That division by the common factor.
You have to
It's
compute
like one
numerator and
observable
denominator
divided by
separately, right?
Sorry.
You have to compute numerator and denominator
No.
separately.
Here you just compute the numerator. That's it.
Then no.
You compute the expectation value.
Yeah, expectation
But you have to know
value.
how to
That is.
weight- But you have to know how to weight the Monte Carlo, right? If
So-
you compute the expectation value of 1, you get the partition.
No. You compute the expectation value as a numerical operation. Okay. And each entity, it comes with that division of partition function.
But let's say you computed the expectation
No, but
value.
that's
of
not
1.
the right path integral you want to compute. You don't want to normalize every instance of your sum, right? we want to normalize at the very end. The quantity, the denominator is also a separate integral. The quantity numerator is separate integral.
But
So
it's
I'm
a
missing
number.
something, I'm sure.
Partition function is a number, right? Just a number.
Yeah, it's an integral, so it's a number
It's
also.
a number. You're multiplying by 1 over that number.
Yes, so in particular you want to compute that number or not?
And if you
I mean, I'll
compute
probably
numerator and denominator
miss that.
separately, you just want to compute the expectation value of some quantity. So you compute,
Yeah.
but there's some weight. But what that I can see you don't compute numerator and denominator separately. Because but what I'm not understanding is why you can't compute the expectation value of 1. Which will give
So
you.
how do you see that? You cannot.
Oh, you're saying expectation value of 1 will be 1 is normalized to 1.
So expectation value
Of 1 is probably normalized to 1 in how you're computing.
Yeah, if you measure 1,
I
yes, you will
see.
get
1, you get 1. I see. So that's why you don't compute. So I think the point is he's saying you're sampling some quantity, but you don't know, how, if you really sampled 1, what you would get. So let's say I measured some quantity at 10 different points. And I know its expectation value is just that value of those 10 different points divided by 10. Without knowing.
Where did that take? Where did that denominator come from?
I sampled at 10 different points, so 10 different points. So that I just know the expectation value. Without knowing how many points there were in the whole unit.
Oh, because the sampling has been done with the
Yeah, so I can sample like 100 points and get something without knowing what the total population is. The partition function is total population. I don't know if I said something wrong, but this is what my understanding is.
Yeah, I think that makes sense. I cannot find anything.
Yeah.
Okay, very good. So let me continue. People may be getting
Okay, so yeah,
for.
it's not now please.
Okay. So okay, all right. So now let's look at what is already known for this theory, okay, A, in 2 dimensions, 16 supercharged. So this is the phase diagram of this, when we put this theory on a torus. So here we have the region where the gravity dual exists, okay? And here this is the high temperature region, where as you increase the temperature of the system, fermions decouple from the system, and you can treat this as a bosonic quantum mechanics. And we have some results coming from here. There is a phase transition between confined and deconfined phases, and we know what the shape of this bubbles. Okay, that is known. And again, in the gravity, in the region where the gravity dual exists, there is also a phase transition, and this has been computed from supergravity and also using Monte Carlo simulations. So this is my work from back in the days when I was a PhD student with Toby Weissman and Santa Petrel. So we tried to reproduce this using lattice, and we got something similar to this, and we verified the prediction of supergravity. And there has been another work which is fairly recent, again trying to reproduce this, okay, with better lattice, larger number of colors, etc. So here in this work, what we are seeing is instead of going like this, it is actually turning over. Okay, the 2-dimensional theory with possible changes. So it's here it is kind of okay, following the pattern, but in the gravity dual, that region, it is actually drastically different. Okay, so again, it is trying to saturate to some value. So that is, so the behavior is drastically different from what we see for the theory that has well-established dual, the 16 supercharged.
What's alpha?
Sorry,
What's alpha?
what's happening?
What's alpha? What's the axis?
Oh, alpha is the aspect ratio of the lattice. How rectangular it is. Changes the shape of the torus.
Increasing alpha is increasing temperature or decreasing temperature?
It is connected to, so we can look here. Okay. So R tau, increasing R tau means decreasing temperature. R tau is inverse temperature. Yeah. So here, this is the region where supergravity should be valid.
So you don't know if supergravity is valid at all, right? In this sense.
Exactly. If it exists, if somebody has constructed something. So this is the question we are giving to supergravity people, string theory people who construct these solutions. Okay? Because it's a much simpler thing. So the question is, what do you see there? Okay. So the result is it rules out possibility of topology changing transition if it exists. Okay? If some blank object exists, there shouldn't be any transition where the topology is changing. That is what our conclusion is. That is gauge series. Okay.
Somewhere along the way, what this case you're saying strong coupling, where you said supergravity might be valid in something.
Yeah, strong coupling of the gauge theory, where one can do weakly coupled gravity calculations.
So when you say strong coupling, it means strong coupling at some scale. At what scale? At the temperature scale.
No, we are talking about the Tooth coupling.
I know, but it's not a
Tooth
conformal-
coupling order 1, so we had to,
It's not a
again dimensionless variables. So I would say strong coupling would be larger or tau. Okay.
So I'm asking a much more basic question. Because it's not conformal, eventually, high enough deep enough in the UV, the coupling always goes to zero.
So you said something more conformal.
It's not conformal.
It's not conformal.
So because of that, if you go to deep enough in the UV,
Yeah.
it always goes to zero. So when you say it's strong coupling, it means strong coupling at some scale, the temperature scale, or what scale?
Strong coupling with respect to, we should take ratios. With respect to temperature, beta.
So
inverse.
at the scale of the temperature, you're saying the tooth coupling you measure, that tells you that is one.
Yeah, around 1 or above. So yeah, the ratio is order 1 or above.
No, not the ratio, I just mean at the scale. The tooth coupling is flowing, right? It's not
But
a
it has dimension, right?
It also has dimension, but isn't it also flowing?
One can measure, one can do lattice calculations of various tooth coupling values. That is possible. But here, what we did is we took the ratio so that it's dimensionless. Okay, now future directions. We can ask, so this schematic diagram was proposed by these famous people in 2006. So Subrata, you were a graduate student at that time. Okay, by Shiraz and others. So this part is incomplete. Okay, and we don't know how, so this is a totally non-pervasive aspect. We can try to complete this using lattice gauge series equations. So that is another question we are asking. Complete this phase diagram.
So which fluid is this?
Sorry?
Which fluid is this?
So this is a bosonic, it's coming from a supersymmetric theory. You remove the fermions, look at purely bosonic part. Again, compactified on a torus. And it should have a phase diagram like this, which would confine and deconfine phases. Okay, for various values of this Rx and Rr. Okay. And here we don't know how the completion happens. So look for this, that is another thing we are investigating. Then study the extent of scalars, which is a set of observables in the system. It tells us about the bound states of the range to gravitational theory. Then another question is, there is a theory that lives in the middle of these two, 16 supercharged and 4 supercharged. There is an 8 supercharged theory, okay, which also admits this twisted formulation. So we can ask what happens to that theory, which is in between these two. So there is another question we are trying to answer. Okay, so that's it. So these are the collaborators. So the very interesting thing is these institutes, they are in 4 different continents. So it's like a continental collaboration. Yeah, so with that, let me finish.
So thank you. So we already have a lot of discussion, but maybe 1 or 2 key questions.
Okay, so I am around, we can discuss.
Okay, so then thank you very much, Anosh.